Good morning, good afternoon, good evening, whenever you're watching this video, hello and welcome to section 4.5. There is no day 2, it's just section 4.5, there's only one day. And we're going to find the local linearization of a function. This can also be called linear approximation or tangent line approximation. Those are all words you should consider doing problems like this. And basically, all this is an Algebra 1 problem, writing linear equations. The only thing that's different about this is we have to find the slope, which means we take the derivative and find the slope because the derivative is the slope of the tangent line. And all this is writing lines, and you're going to see that in just a minute. But it takes on a little bit different look when you're finding the derivative. So if you have a tangent line to a curve, and it's at a point, xy, then we write the linear equation in point slope form. Now, if you're doing a multiple choice question and the answer is in slope intercept form, then you're just going to have to, simplify your equation. But if you're doing a free response type question, this is the format you're going to use so that you don't make any math mistakes. All right, this is called linearization to write the line equation, a local linearization, linear approximation, or tangent line approximation. Now, this is basically a linear equation. Let's see if I can get a little room to show you. Y equals, this is M, this is X, and this is B. All right, so it's the same thing as a linear equation, and that's just a fancy way of writing it. I put this on here because this is in your book. And hopefully, as we're going along these lessons, you're also looking at your book and trying to get some information from there. You've got to use all your resources. Anyway, the closer you get to this point A, which is the X value of your point, if you zoom in on any of these continuous equations that are differentiable, if you zoom into that point A, you will see a tangent line. And you can do that on any point in your calculator, and you will see that as your calculator gets closer and closer, that curve starts straightening out, and it looks like a tangent line. And so this L of X, which is the same thing as Y, is the approximation of the linear equation or the tangent line. All right, let's do some examples. Find the local linearization of this function at x equals 0. Okay, so we need two things to write the equation of the line. The first thing is we need a point. So we have the x part of the point, x is 0, and if we put a 0 into our y equation, we get the square root of 1 plus 0. Therefore, the y value must be 1. And there we have our point. Next, we need our slope, which is the derivative of x. And actually, it's going to be the derivative at x equals 0, because that's our point is 0. So let's rewrite this equation, 1 plus x, and make a rational exponent, 1 plus x squared. And also, we would also multiply by the derivative of the inside, but the derivative of the inside is just 1. So I skipped that part, but that's actually technically what you're doing. And then we're going to take the derivative of this. So we multiply by 1/2. We subtract 1 from the exponent, so we get negative 1/2, 1 plus x. Now, I'm going to rewrite this derivative because some people, now you can use your calculator to calculate this, of course, unless it's a non-calculator problem. So I'm going to rewrite this equation using radical and also using the fractions. So this is the same as 1/2 times the square root of 1 plus x. A lot of people make a mistake on this particular problem right here because they don't put that 1 plus x in the denominator. The negative 1/2 exponent means that it is a square root, and it means that it's below the line. It moves to the other side of the fraction bar. So that's our derivative equation. If we take that derivative equation and put a 0 in for x, we have 1 over 2 times 1, so that's just 1/2, right? So m equals 1/2. Now we just need to write the equation of the line, and then we have one other part to this problem. So y minus 1 equals 1/2 times x minus 0, or just x. And so if you were asked to write in point slope form, you get y minus 1 equals, wait, I'm going to add 1 to both sides. So you get 1 equals 1/2 x plus 1. All right, that's just writing the equation of a line. And here, notice I simplified this. This would really be x minus 0, but you don't need that x minus 0 because x minus 0 is just x. So either one of those formats is good. Now it says use the value of the local linearization to estimate the value of y at the point x equals 0.1. So y equals 1/2 when x is 0.1 plus 1. So what do we get? 1/2 times 0.01. We get 1.05. That's what the second part of this problem asks. Use the value of the local linearization, which means use the equation of the line to estimate the value of y. Okay, next example. We have a little bit more fun equation, but they've already given us the point. So we know that the point is 0, 1. We just have to find the slope, which is the derivative. Okay, so same problem as the last one, just a different equation. So the derivative of this equals 0. Derivative of sine is cosine of x. So if I plug a 0 in for x, because that's my x value, I get cosine of 0, which equals 1. So that is your slope value, 1. Therefore, your equation is y minus 1 equals 1 times x minus 0. And that's just the same as add 1 to both sides. I'm going to write this in slope-intercept form, but you don't really have to unless it is asking you to do that. You get 1x plus 1. All right, so that is your equation. Then the next part becomes quite simple because you have the same thing, finding the local linearization when x equals 0.1, and you get y equals 0.1 plus 1 equals 1.1. Sweet. Next example. Here we have something that might actually challenge us a little bit. Okay, we have a point, 3, 0, and we need to find the derivative of this implicit function. I love these. Okay, so we have x cubed plus x tangent y equals 27. Two things. This one, you're going to have to use the product rule for, and also you have implicit, so you're going to have to multiply times dy dx. So let's take the derivative of this equation to find our slope. And we don't actually have m yet, so we're not going to put an m equals there, but to find m, we're going to take 3x squared plus. Now we're going to have to do the product rule for x tangent y, so we'll put that in here, equals the derivative of 27 is 0. Don't forget that. All right, so product rule, u equals x and v equals tangent of y. Derivative of u equals 1. And the derivative of v equals, the derivative of tangent is secant squared y, and we also have to multiply times the derivative of the inside, which is dy dx. So let's write this product down. Tangent of y times 1 plus x secant squared y dy dx. Now in this case, our slope is the same as dy dx. So we need to solve this equation for that when x equals 3 and y equals 0. So instead of simplifying this, I'm just going to immediately plug in a 3 for every x and a 0 for every y. So we have 3 times 3 squared plus tangent of 0 plus 3 times secant squared of 0 dy dx, and that equals 0. To simplify this, 3 times 3 times 3, that's 27. Tangent at 0 is sine over cosine, which is 0 over 1, so that's a 0. And we have 3 times secant squared. Remember that secant is 1 over cosine of 0 squared. Cosine at 0 is a 1, therefore secant squared at 0 is 1. All right, so you should know that secant squared equals 1 over cosine of 0 squared. Okay, so know that. All right, times dy dx equals 0. Now we need to get this dy dx by itself. So in order to do that, let's subtract 27 from both sides. It's a minus 27. And then we can divide by 3. And that leaves us with dy dx equals negative 9. If you don't believe it, try it yourself. All right, so we have, that's our slope. And our equation of our line is going to be y minus 0 equals, slope is negative 9 times x minus 3. So that is our linear approximation. The second part of this problem asks us to find the value of y when x equals 3.1. So now we're just going to plug in 3.1. 3.1 minus 3 equals 0.1 times 9, which is negative 0.9. That brings us to the end of our examples on linear approximation and local linearization or tangent line approximation. A big part of this lesson is just knowing what those words mean. So be sure that you remember that, make note to understand those words for the AP exam, which is right around the corner because it is almost summer. Welcome to, this was section 4.5. Next up will be related rates. Thank you for tuning in. Signing off.